In this video, I'll be discussing magnetic resonance spectroscopy and the theory and principles behind this spectroscopic technique and its applications in identifying atomic and molecular structures in chemical species. So for the background, atomic nuclei, certain of them react differently under applied magnetic fields. This is seen commonly in nuclei such as hydrogen, fluorine, and isotopes of nitrogen and carbon. They can occur in phosphorus and silicon as well. It's just dependent on the certain isotope that's used. Nuclei, all of these ones share a common property of a non-zero net magnetic moment. This is a quantum mechanical property referred to commonly as spin. This is an intrinsic form of angular momentum. Now, because this property arises from the odd number of protons and neutrons in the nucleus, the electrons distribute themselves in a spherical manner where this arises a dipole moment, where we have a positive and negative pole. This allows the atomic nuclei to act as a tiny bar magnet. And bar magnets under a magnetic field, they align themselves in the direction of it. So if we place an atomic nuclei around in a magnetic field, it's seen that it precesses around it in the z-axis in a circular path. And this is commonly seen in a system as a gyroscope, where you have a gyroscope's angular momentum precessing around a gravitational field due to the force being applied down on it. And you can see this where the magnetic ratio or the magnetic moment is equal to the magnetogyric ratio and the angular momentum. But because we're studying the nucleus's angular momentum, quantum theory states that angular momentum has to be quantized. And this is due to the eigenstates that the nucleus exists in, where only these possible values of the nucleus exist. So if we're looking in the case of hydrogen nuclei, we can only see that the possible quantum numbers or eigenstates are plus 1/2 and minus 1/2. So these are the only two possibilities this nucleus's spin can be in. If we look for the actual vectors where we see the magnetic moment precessing around the z-axis, this is for the negative 1/2 spin state. But we can also see there's an inversion, which is this Larimore precession, which is just the spin around a external magnetic field. We can see an inversion spin flip. Now, if we're considering the energy of this system, for originally, these eigenstates are what we call degenerate, meaning if there is no applied magnetic field, this plus and 1/2 minus spin state, they are the same when there's no energy applied. However, as we apply a perturbation, which is the magnetic field, this perturbation is able to change the energy states between them and lifting this degeneracy. This is known as Zeeman splitting, where we're splitting the two energy states, and the energy given by them is delta E is equal to the negative magnetic moment vector dotted with the magnetic field vector. The vector dot product returns a scalar, which makes sense for our energy term. This is the Zeeman splitting effect, where we can see the spectral observation, where we can detect changes in energy based on these spin states. And now that we've defined our vector components and energy of our spin states, we can now obtain a measurable source of interaction. We can do this by applying another perturbation of the form of an electromagnetic energy, also as a radio frequency pulse. What radio frequency pulses allow us to do is we can transition spin states from higher to lower energy, and this is due to the absorption of the radio frequency by the atomic nuclei. This causes each nuclei to have their own source of interaction, which can be measured. The strength of the frequency can vary from anywhere between 60 to 600 megahertz and even cases of 1.2 gigahertz. This is due to, if we refer to the previous slide where the energy diagram of the Zeeman split, we can see that as B field increases, delta E also increases as well because we're applying some proportional energy. The radio frequency needs to be either greater or equal to the change in delta E to compensate for that spin state flip. Now, if we see the pulse sequence For general cases of 90 to 180 degrees, we can see that in certain experiments that we want to do, but if we consider the 90-degree case, we apply a spin flip because of the RF input. It causes its spin state to flip, and then we decay this energy and we allow it to precess back to its original energy state. And we can measure all of this interaction through a receiver coil. So if we consider the interaction from the perspective of the receiver coil, what's happening is as we apply an RF pulse, the nuclear magnetic moment, which is mu, is in a state of non-equilibrium when the RF pulse is applied. This is applied at the Larimore precession frequency, so this is the precession around the magnetic field. If we apply it at that frequency of the nuclear spin, it has a non-zero vector component, which means is if we have a charge in a circular path, this induces its own magnetic field due to the right-hand rule. And if we know from Faraday's law that the EMF, or induced voltage, is going to be equal to the negative number of turns times the change in flux over the change in time. And this is how we can measure this changes in energy. And we can see here where we apply a radio frequency pulse, we're allowing our spin flip to happen, and as that precession happens, it's an oscillatory voltage in the form of a sinusoidal pattern, which is known as the free induction decay. So now that the FID data has been obtained, we need a way to convert this signal into actual spectral data, and this is with the frequency domain. The frequency domain actually gives us the information that our atomic nuclei absorbed and re-emitted this energy, and this is the key signature of nuclear magnetic resonance. However, for us to go from the time domain to a frequency domain, we need to use a mathematical function known as a Fourier transform. What a Fourier transform does is we take our time domain and we're taking an integral of it and we're returning back the frequency domain, and we're doing this along each point in time. Now, if we see here on the left, the arbitrary function, we're modeling it by a combination of cosines and sines. Now, this combination, we can split them up in the number order of terms, and this gives us the relative frequencies or intensities at which the signal is being measured at. And this will give us our resulting frequency domain. In a math operation, the computer will typically do this by a summation, where we're summing each point of the time domain, and we're going to plot that in terms of the frequency. So if I'm going to identify the molecular structure of hydrogen in water, what I'm seeing here is I have an increased signal around 300 Hertz. And this is typical for hydrogen nuclei in water because they're absorbing that RF energy in this certain frequency range. Now, this is due to the effect where if I have my spins from both hydrogens, they're constructively interfering with each other, and this is buried in the free induction decay. When you apply a Fourier transform, you'll see only one peak around 4.75 ppm, or parts per million. This is relative to sample concentration, but you can also see this present in the frequency domain. Now moving on to a more complex structure where I want to identify carbon in an organic compound. Here I have N-propylbenzoate, where I have a benzene ring attached with other aliphatic bonds. Now, carbon-13 nuclei, they react differently under applied magnetic field is because they have an irregular number of neutrons. Carbon-12 is not magnetically active because there is no spin that's induced with it. Now, the disadvantage of this is that you have a much lower sensitivity other than hydrogen, and this is because there's a lower abundance of carbon-13 isotopes that are present in organic structures. Only about 1.1% of carbon-13 is present and NMR active. Now, the low abundance of this also rises to a lower gyromagnetic ratio for carbon-13. That's also affecting the signal-to-noise ratio that we see here. There's a lot more noise that we're observing from the other surrounding elements. However, if we average more and more scans, we can see the effective contribution of each carbon atom. Now, this is due to an effect called spin coupling. Spin coupling refers to where we have a magnetic interaction of other magnetic environments, and this is because hydrogen is exerting its own spin. Now, if we consider a benzene ring where we have a cyclic motion of electrons, it induces its own magnetic field. However, because we're applying a magnetic field as well, this effect increases because of Lenz's law, where the flux is changing through a coil, in this case the benzene ring, where what we're doing is we're decoupling these spins because we're detaching the spin interaction between this carbon atom and this hydrogen atom. And then we can see that the carbon atoms are present around for N-propylbenzoate in these respective regions. So those are all the basics on NMR spectroscopy and its usefulness in identifying molecular structure. Thank you for watching.